So welcome everyone. Today we have amongst us Dr. Soumyajyoti Ray. He's going to talk about computational material designing and like particularly keeping the theme of sustainable development in mind. So Dr. Ray did his PhD from University of St. Andrews, and during his PhD he held prestigious EPSRC UK fellowship as well as a doctoral grant from Max Planck Institute. After his PhD, he had worked for his postdoctoral uh, years at TU Darmstadt, Germany and CEA Grenoble, France. And he has been with us since 2016 at IIT Patna. Among various things, he likes to travel, write, and his work spans a wide area of topics. So if you look at his initial papers, those are on a very exotic phase of matter called vortex phases. So he has a PRL early in his career on, and he has many more papers, but this was one of the characteristic uh, piece which I personally like a lot. And after that, he had been working on a wide variety of systems. When this iron chalcogenide and iron arsenide work started, he also made some important contributions to that and reviewing a volume of work there. And after that, he has been working on topological materials, materials for sensing applications, 2D materials, you name it. And more or less, he had either done both theory and experiment on these classes of materials, or has primarily used computational designing tools or like techniques to predict novel properties in material systems which are useful for applications. Um, Dr. Ray has also been serving as the PhD coordinator of the department among several other key institute positions, and he's father of a lovely child. Yeah, Dr. Ray,
Yes,
please.
yes. Okay, yeah. Thank you very much for the nice introduction. And I didn't know that I have so many good qualities. Okay, thank you. So, and thanks to the organizers, of course, like including Dr. Ajay Thakur and Dr. Manoranjan Kaur, and to the audience for your time. So, since I believe that you all are kind of at the end of the day, so without wasting much time, let me start. I hope my voice is audible, right? Yes. Oh, hello.
Yes, it is perfectly audible
Okay.
at my
Okay.
end, and definitely it would be
Okay.
as well.
Okay. 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 Okay, so the theme of the presentation today is computational materials designing and sustainable development. Since this is the theme of the this particular workshop, so here the plan is that I'll first talk about uh, how sustainable development is being kind of created and how it is fueled by different materials development, and subsequently how technology is also coming up in between. And then later I'll talk about how computational techniques could be useful in order to find different materials, and or let's say engineered materials with different properties which could be useful for specific applications, and how they can supplement experimental works also in some cases. So and then I'll talk about some of the results which we have got in kind of let's say past years, so that I'll also highlight towards the, let's say, end part of this presentation. So now let's start. So here, when we talk about sustainability, so this is something which is part of our lifestyle also. For example, if you look at this slide here, so on top you can see that this is a kind of like power plant where quite a lot of smoke is coming out, and clearly we all need power, and for a country like India, almost more than 60% of the power is coming from this fossil fuel burning. So this essentially creates quite a lot of environmental pollution, and that is harmful for our planet in the longer term. And in figure B, you can see there is quite a lot of trash material, so mostly plastic and other waste materials, they are dumped onto some particular area. So essentially these materials also are going to be part of some waste materials which are not going to kind of like decompose very easily and help our environment. So we need to find solution for both these types. Okay, so for example, in the first case scenario, when we are talking about power generation, then we can think of using alternative sources of energy like solar power and photovoltaics specifically, that can essentially give us quite a lot of pollution free power and cut down the pollution in that way. And in the second case, we need to recycle quite a lot of materials, and that way we can reduce the generation of plastic and other waste materials, which essentially creates more pollution. So this way it's kind of a combined job. It's not only replacing but also recycling. Now, here we'll talk about how materials are kind of playing a role in this process. So here in the top panel, you can see this is a cartoon of an electrical vehicle which is being charged from a power station. Now, if you imagine like 10 years back, probably we are not that much familiar with electrical vehicle. I mean, people would have a hard time believing that a battery can power a four-wheeler vehicle and that can drive for hundreds of kilometers. But nowadays it has become a reality. Now, what has changed in between? The main factor what has changed is materials development. So the materials which are used earlier for energy storage, they have a limited storage capacity or energy kind of generation capacity, etc. However, over the years, the materials development has been phenomenal, and as a result, you can see here that in this figure in the middle here, this energy density for lithium ion batteries have been kind of plotted as from 2008 to 2020, and you can see there has been almost like a 9 to 10 fold increase in the kind of storage capacity. So that is essentially possible because there is a huge development in the materials property and materials which can store energy, and that essentially fuels the technology. And as a result, we are now going towards electrical vehicle which will replace the conventional, let's say, petrol or diesel based vehicles. So that way all these things are there in different roles in part of a, like, basically, let's see, if we think of it like a complete cycle, then they are playing their role in the entire cycle in different capacity. So now in the bottom panel here, you can see that there is some smartphone. So it's an iPhone which is here. Now, over the years, the size of these phones have been reduced quite hugely, and that is possible because there has been huge development in the design of the chips which are actually running this phone. So this same is true for our laptop or touch screen or any electronic kind of like devices as such. However, if we think fundamentally that everything here is mostly coming from silicon, and basically here you can think of like this chunk of silicon, and that is essentially kind of like is staying at the heart of these chips, which are microprocessors, etc. So which are basically powering up these phones. Okay, so what we are essentially we have done over the years is that, like, the material fabrication process and the kind of like design of different transistors that have improved quite hugely. So here actually there's a graph, you can see how things have changed over the years. For example, this is this famous Moore's law. So here it plots the number of transistors on a microchip, with a number of years. So this graph actually covers from 1970 to 2020. So this is basically an empirical law which has been predicted by Professor Gordon Moore, and the idea was that what he said is that the number of transistors are on a particular chip is going to get doubled in every 2 years. And here, if we look at basically over the years, more or less the same trend has been kind of followed. So instead of 2 years, it actually came out to be like 18 months. But if you look at the numbers here, so in 1970 there used to be something like few thousand transistors, but now is while we are sitting in 2020, there are like probably transistors are in count of like 10 to the power 9. Okay, so it's in billions. So the number of transistors have increased while the size has reduced. So that has essentially become possible because of materials development, and of course the way these transistors are being made. So here now, if we talk about kind of sustainability, so here what is happening is that as we are increasing basically the number of transistors, the size is being reduced. So as a result, what is happening is that there are more and more number of transistors as are being kind of like, let's say, condensed into a given volume. And essentially, if you see this graph here in the inset, then we can see that we are almost kind of close to, let's say, below 10 nanometer, like 6 to right now. I think we are all like at 6 to 8 nanometer node. So here, basically, the technology which is being used to develop these transistors or microprocessors are kind of going to hit almost the end limit, because if you think of like 5 or like 6 to 8 nanometers, they are like of atomic scale. So you cannot, like, one cannot keep up doing this scaling forever. Okay, so but however, there is a big need of let's say mobile phones and higher computing power, and let's say more memory, etc. So how to survive? So here, in terms of sustainability, what we have to do is that we have to think of new classes of materials, or the design has to be changed. So that way, basically, we can still keep up the trend, and also kind of like the requirement will be fulfilled. So materials development is very much necessary here. Now, this is another example. So here, if you look at like how materials development have played a role, so this is a graph of solar cell efficiency, how it has increased over the years. So here you can see, like in 1975 or 1980, this efficiency used to be below 4%. However, over the years, the efficiency have increased drastically. Of course, there are different materials which have been used here. And other than that, of course, there are multi junctions, like architecture has changed also. And right now, there are solar cells which are having efficiency almost close to 50%. So in terms of technological development, the efficiency is almost 10 times. And that is possible because a materials development, and also simultaneously how we are designing the cells. So that way, basically, the trend can be kept alive with keeping these factors in mind. Now, how can we do such materials development? So here is a very rudimentary picture. So in the laboratory, usually we do develop or let's say prepare materials either through some let's say synthesis route. So here you can see this first figure here. That kind of tells us, like, if you are mixing few constituent powders and then kind of like going to heat them and sinter it at a certain temperature, so that way you will get a particular compound which you are going to make. Or alternatively, you can do a thin film deposition. So here typically what happens is that you have a vacuum chamber and you pump it down, and there will be some source materials which will be kept here, and then you heat it with in this case it will be an electron beam. So this electron beam will heat up the source and the materials will be evaporated, and here will be a substrate. On top of that, these materials or these atoms which will be evaporated from here, they will be deposited. So they are like some way of materials development, and essentially after these things are done, then you will do some sort of structural characterization, typically like an XRD measurement, in order to confirm whether the crystal structure is there or not. So this is one way of doing these things. Now there are computational methods also where it is possible to predict materials and their materials properties. So for example, here you can see in the bottom half that there are several graphene and graphene derivatives have been are there. So they all have kind of like these hexagonal unit cells. However, there is some small difference between them. And what computationally it is like such materials are handled is that there will be some structural optimization which will be performed, and once that is done, then the electronic properties etc will be calculated. So here actually on the right hand side you can see that if we have some sort of a, let's say, cells like material structure here, and then in the reciprocal space it will look something like this. So here the center is this gamma point, and there are this zone corner, and then this edge center, and we can get the band dispersion or band structure here, and from there we can talk about whether the material is uh, let's say semiconducting or metallic or insulating, and then what will be the, let's say, carrier mobility or effective mass, etc. So there are many other things we can talk about from this kind of diagram. So both these processes are like kind of methods are there in practice. Now it's not that like one is better than other or one is kind of like giving better efficiency, etc. Both are kind of like going together simultaneously. So let's say computationally, if one predicts a material, then that has to be experimentally verified. On the contrary, experimentally, it is not possible to try and test every single kind of structure because that is a huge task. So that is where this like, let's say, computational tools comes in. So what they do is that they kind of sort out several material structures, specifically in low dimension. I'll talk about this in next few slides. So out of several material classes, it predicts which of these materials are likely to survive or likely to be experimentally kind of discovered. So then experimental works are being performed towards those likely materials which have a higher probability of synthesizing. Okay. Now, before getting into that, let us talk about materials and dimensionality. So here what happens is that, so when we are talking about materials, and typically the materials are associated with dimensionality because the materials could be of different physical dimensions. So here I have taken the example of graphite, and from the left to right you can see this is carbon nanotube, then which is an one-dimensional object. Then there is graphene, which is a two-dimensional sheet of carbon, and then graphite, which is a three-dimensional basically form of carbon. So typically, you know that graphite is available in our, let's say, day-to-day life in our, like, these pencils. This tip is graphite. Now, what happens is that this material graphite is three-dimensional. So here the crystal structure is such that, so there are individual layers of carbon atoms which are stacked together vertically, and the interlayer attraction, or let's say force between different layers in the third direction, is much smaller compared to the in-plane attraction force between the atoms. Okay, so what happens is that, like, in plane is quite high compared to the out of plane force. So this is a van der Waals force which is acting between different layers. Now, as a result, what happens is that if somehow mechanically we try to force one layer to kind of like slip from the next layer, then it is possible to kind of separate out individual layers from such a 3D block. So this thing is difficult to do for, let's say, a block of iron as such. Okay, but for graphite you can easily do it. So that single layer, so typically it is done through like using a scotch tape. So you use this tape and then kind of put it on top of this graphite block, and then a few layers of this carbon atoms will come up, and then you repeat this tape few times, and then you will end up with one or two layers of these carbon atoms. So that is called as a two-dimensional form of graphite. Now, here there is a big change that happens. So graphite essentially is a three-dimensional structure. So the crystal structure and the material properties completely behaves like a three-dimensional system. However, when you're talking about graphene, there is a 2D form. It has a completely different kind of, let's say, physical form compared to its mother compound. So as a result, what happens is that we call it as some sort of like a 2D crystal. Okay, so the behavior or the physical properties will be completely different from the mother compound itself. For example, graphite is not that much kind of like, it's slightly insulating, but graphene is very highly conducting. Now, if we are going from 2D to 1D, then we can see the behavior will again be different, and from 1D we can go to 0D. So the way we are talking about dimensions, the material properties also do change quite a lot. So let us see how does it work out. So here is a graph which actually talks about that if the materials are in 3D form or 2D form or 1D or 0D, there will be some type of quantum confinement into picture. So for example, when we are talking about a 3D material, so then as such, all the dimensions are, let's say, of macroscopic scale. So as a result, if we are looking at the density of states here as a function of energy, then we can get this kind of, let's say, parabolic dispersion here. However, when we are going to a 2D scenario, then what happens is that there will be a confinement from one direction. So here in this case, it will be from the vertical or Z direction. And as a result, the density of states, which was earlier a parabolic curve, now it will become a step-like function. Okay, so those of you who are not familiar with this density of states, so it's basically, let's say, the number of available states per unit volume at a given energy. So essentially, higher will be the density of states, higher will be, let's say, the available kind of availability of, let's say, conduction or even other properties that will be affected because of this. Okay, so now here when we have 1D confinement, then basically this step-like features is coming in. So as a result, what is happening is that here we are having states at a particular energy only. Now, if we increase the order of confinement, for example, if you say 2D confinement, that means the material will be one dimensional. So that is kind of like a wire kind of structure. So you can think of carbon nanotube in this class. So here, since the confinement order is much higher, so what happens is that here this density of states here, it becomes much more sharper and peaky. So rather than having a continuous distribution, now you will have higher density of states at some given energies compared to other energies. So as a result, what happens is that, let's say, if we are using it for conduction, then you will get conduction at some specific energies. And then if we are confining the structure from all three given direction, then the final structure will be 0 dimension. So we call it as a quantum dot. So in this case, the degree of confinement is highest. So as a result, what happens is that the density of states, it becomes like a delta function. So you only have states at certain given energies. So as a result, the entire system, it kind of becomes quantized, and that is why a lot of interesting features come out from this quantum dot system. So essentially what happens is that the order of confinement, it determines the electronic properties, and those electronic properties, it kind of plays a role into the properties that we see in physical form. So be it optical properties, be it magnetic properties, be it transport properties, mechanical properties, whatever you need, like thermal behavior, etc. So essentially, how the states are being distributed in different energy level, that determines how are those properties are also going to play out. So now here we are going to particularly focus on this 2D materials. The reason is that basically these materials have quite a lot of novel functionality. So what do I mean by this is that, let's say, compared to its bulk counterpart, these 2D materials, they do offer interesting physical properties, and that can be used for making different devices or let's say various applications. So typically they're like superior electronic properties which you get. So that can be useful, for example, like sensing, then also kind of like photovoltaics, or also in different energy applications, then like optical kind of like, let's say if you are going to talk about different optical devices there also. So these 2D materials have a lot of variety of properties, and that are kind of very much interesting in terms of, let's say, physical applications. So here there are a few examples of the most popular 2D materials. So here you can see that this is graphene. So this is from carbon atoms. Then there is phosphorine. So this is a single layer of phosphorus atoms. And if you compare these two, then you can see graphene has quite a bit of like planar structure. And here the plane of this phosphorine layer is not entirely flat. Rather, there is some sort of like ups and downs, kind of like this hill and valley kind of structure. Okay. Now, then there are other materials also, like compound materials like boron nitride. So this is made up of boron and nitrogen. They are kind of sitting in alternative positions. So it has a similar type of crystal structure with graphene. But electronically, if we look at, then the properties are vastly different. For example, graphene is a semi-metal, but this boron nitride is an insulator. So the material properties are also different. Then there is this transition metal. Hello. Then there is this family of transition metal dichalcogenides. So this is typically like molybdenum disulfide, tungsten disulfide, etc. So here they are quite useful for optical applications mostly. And then there are other materials like this boropene and this general family, which is called as MXN. So essentially there are different classes of these materials, but they are hugely varied in terms of electronic properties, structure, material configuration, etc. Now, how to deal with them? So here also there is another interesting part with these materials is that the materials engineering can be done quite easily here. So the idea is that, let's say if we are talking about any two different 2D materials and then we are putting it on top of each other, then the heterostructure which will be created as a result of that, that is called as a van der Waals heterostructure. Now, this heterostructure itself will offer properties which will be different from the constituents. For example, if we are talking about a graphene and hexagonal boron nitride heterostructure, then the heterostructure will show a property, or the properties which you will measure will not be either identical to graphene nor identical to boron nitride. So it will be different. So that way there is a big option of materials engineering, that you kind of, let's say somebody wants a material with some particular band gap, with some carrier mobility, then what one can do is that one can try to think about what sort of material combination can give this sorts of behavior. So that way it's a materials engineering which happens at the atomic scale. So here we are talking about entire 2D sheets. Now, there are few additional advantages of these materials. So one is that they have large surface to volume ratio. So what do you mean by this is that since they are only one sheets of atoms, so these atoms which are present in the materials, they're essentially all on the surface. So as a result, if there is any excitation that is present in the surrounding, so it could be an electromagnetic interaction, it could be some molecule, it could be some charge, then they are directly going to interact with these atoms. So if you think of a 3D structure, a large amount of material is confined inside. So there are only a certain amount of surface area. However, here the surface area is much, much more. So as a result, since the atoms are directly interacting with that external entity, so the response which will be generated is also going to be quite significant. And that property is being exploited for developing quite a lot of devices. For example, particularly sensors are something which 2D materials are very popular for. Okay, so this is about heterostructure. Now, recently there has been another new area which has opened up, that is about twistronics. So what happens is that, let's say if we are taking two layers of graphene itself, and then if we are slightly rotating one layer with respect to the other, then it is observed that the material's property is changing quite significantly. So like this computationally what was observed is that uh, the band structure itself, it changes. So what happens is that, for example, in the case of graphene, you have very sharp bands. So there are like Dirac fermionic states which are present there. But in the case of this bilayer structure, when we are rotating it by, let's say, certain small magic angles, then the bands become flat. So as a result, the effective mass increases hugely. So there is some strong electron correlation which comes into picture, and as a result, the material offers some property which was completely absent, or even like no one has thought about. For example, in the case of bilayer graphene, when it is rotated at some magic angle of like I think 1.14 degree, then people have observed the heterostructure can become superconductor. So that is something which was unimaginable earlier. Okay, but however, it is observed that if you rotate it with respect to each other, then some interesting properties are coming up, and there are also like ferromagnetism is also coming up in non-magnetic structures, etc. So there is quite a lot of interesting works which is going on, and people are trying to figure out how that property can also be exploited in order to kind of like tune different materials properties and for different kinds of applications, etc. Okay, so that way basically these material classes offer a lot of interesting properties and materials tuning, etc. Okay, so now what we are doing in computational materials is that here mostly different kinds of modeling tools are used, and then people do perform simulations based on certain theory. So typically these are first principle based calculations, and from the output one can actually predict the material properties. So the idea is diverse. So for example, it could be about discovering a new material, or it could be about explaining some experimental data. So whether the data makes a good fit with a certain model or not, or it could itself be simply determining a material behavior which is unknown or which is not reported yet. So here you can say that this somehow comes in between theoretical and experimental work. So there is a bit of overlap in between them. And recently, because there is quite a lot of work that is going on with this big data architecture, so people are also trying to use different machine learning algorithm in order to automate these things. So for example, there are certain material structures which are available, and if we can somehow kind of train the models, then whether without doing the extensive calculations, it is possible to predict the behavior of a material class, or let's say certain material property, etc. So that will kind of save quite a lot of time and also kind of computational cost. Okay. Now, what is typically done here? So there are quite a few techniques, but here I'm going to talk about only one particular one, of course, because of I mean, otherwise this will go. I mean, this talk will become quite long. So typically when we are talking about these materials, so there are many electronic systems. So what do I mean by many electronic systems is that, like, let's say typically the simplest quantum mechanical system what we know is that hydrogen atom. That is a practical system, and we know exactly what will be the solution of the hydrogen atom. So we know the wave function, we know how does the orbitals look like, and what will be the different energy eigenvalues, etc. So that way we can predict the material properties. However, so as we know that like Schrodinger equation is the one which we have to kind of solve here, and wave function have to be kind of found out from there. Now, as we are going towards a material systems which have more than one electron, then what happens is that the Hamiltonian itself will contain some additional terms. So, for example, let's say if we have more than one electron, or let's say if you're talking about n electron system, then what will happen is that in the Hamiltonian, you can see here that there is basically the kinetic energy terms. There are two kinetic energy terms, one from the electrons and other is from the nucleus, and then there is three electrostatic terms. So here there will be this electron-electron interaction that will come up. So if we think of simply like a 2 electron or 3 electron system, then this picture will be a little bit simpler. simpler. So here there will be this electron-electron interaction term which will come up, and that will kind of make it difficult to find an analytical solution of this equation. So higher will be the number of electrons, higher will be the dimensions, not dimensions, basically higher will be the number of equations which we have to solve, and it is not possible to do it analytically. So one has to kind of make use of different computational tools. Now here also there are several methods people have kind of tried and tested over the years. And for example, like the Born-Oppenheimer approximation is there, then there is Hartree and Hartree-Fock technique is there, then variational principle, and finally the tool which is used quite extensively these days, that is called as density functional theory. So what this theory is does is that basically it is based on two theorems which have been given by these two scientists, Hohenberg and Kohn, and they got Nobel Prize because of this particular development. So the first important thing here, what they have said is that it's not wave function anymore, but rather they are talking about the electron density. Okay, and this electron, and here they are introducing the concept of energy functionals. So the energy will be a function of the electron density itself. So this electron density will be related to the wave function. And here the assumption is that the functional, that is the E, that energy functional, which is a dependent on rho, that will be minimum in the ground state, and whatever value of rho will give that ground state configuration, that will be the ground state electron density. Okay, so in that way we are getting a ground state configure kind of like calculation, or we are predicting a ground state behavior here. So now what is being done here is that, so in very simple terms I'm trying to explain, this is of course a big thing. So essentially the Schrodinger equation here is being slightly modified, and here it is, we are calling it as a Consam equation. So essentially we are mapping this many electron problem into an kind of like one electron problem kind of thing. Okay, so, or one particle problem you can say. So here basically we have this kinetic energy term and we have this potential energy term, but rather instead of having different terms here separately, where we are talking kind of defining it as an effective potential, and that effective potential has several contributions. So there is some external term, then there is this Hartree term, and there is something called as exchange correlation functional. Okay, so that is the major contributor here. And in density functional theory, what it does is that there are different exchange correlation functional, and one can actually think of that what sort of this exchange correlation function is more appropriate for that particular system. Whether, for example, let's say if it's a kind of like a heavy atomic mass, or let's say there is strong electron correlation, then the exchange correlation function has to be different from something which is, let's say, with low atomic number, etc. So how does it typically work? So the way it works is something called as a self-consistent method. So let's see. So let's say you start it with some initial rho, and with that rho, this effective potential will be calculated. So there are three terms, and that will give you this constant Hamiltonian. And with that you will solve it, and you will get some psi. So from that psi you can get the rho. So this is the rho which is kind of obtained after the calculation, and then there will be a comparison made between the initial and final rho. So let's say if they are matching, so in reality they don't match, of course, but let's say they are the difference is within certain tolerance limit, let's say like 1 in 10 to the power 5 or 10 to the power 6, something like that. So you can set up the tolerance limit, then you will accept that whatever initial rho you started with, that is more or less close to the exact ground state solution. So you can go ahead with that. If not, then you will repeat this process. So what you'll do is that you will take the rho n, and then you will repeat the entire process, and you will keep on repeating it unless the difference reaches the convergence criterion. So once, so that can take a long time, depending on like what sort of systems you're working on and how much is your like computational power and what is the parameters that you're using. So now once let's say it is done, so you are ended up with, so you get the solution, then from there you can calculate different parameters and properties. For example, like you can calculate the ground state energy, force, etc. Okay, just give me 1 second. Okay, sorry. So now from that you can actually elaborate this calculation, and you can calculate electronic properties, then magnetic properties, then optical properties, transport behavior, thermal response, etc. So here I have plotted kind of like a few graphs which I have taken from the internet. So one thing that you can plot is that this is the band structure. So here you can see these are the energy bands which and they are kind of like there's quite a lot of curvature and slope, etc. So I mean, very simply, if you look at, then this zero is something which is, let's say you can call it as close to Fermi level. So here there is this red and black line. So they are, I think, spin specific. So one is probably spin up, another is spin down. And then so here you can see there is almost these bands are touching. So here you can say this material will not be, of course, a gap structure. So this is not semiconducting and insulating, rather it can be metallic or it could be semi-metallic also. So you have to look at the dispersion here. Okay. Then it is possible to talk about the magnetic behavior. For example, the magnetic moment can be calculated, and here this graph is plotted here, where this magnetic moment, which is predicted through DFT, that has been compared with the experimental values for different transition metal atoms here. So you can see like cobalt, then chromium, iron, manganese, etc. And you can see they, I mean, quite a significant fraction of them are kind of like falling on top of this line, which is basically the slope of 1, which means that there is a good 1-to-1 match between these two. Okay, so that way we can say that like the calculations are not giving us very much inaccurate result, rather they are kind of quite close to the actual experimental behavior. Then you can also talk about or let's say find out the optical properties. So here the refractive index has been plotted, and from there actually you can see like if the incoming electromagnetic wave has a state of polarization parallel to the c-axis or perpendicular, then how do the trend differ from each other. And then here also it is possible to talk about thermal conductivity. And here for this particular case, people have used some diamond and copper composite, and they have applied probably some PP. I'm not exactly sure what is this, but anyway, you can actually see like how this thermal conductivity is behaving with a different temperature that has been kind of like estimated and plotted here. So there are quite a lot of useful information one can actually find out from here. Okay, so now recently, let's say there is a big push on something called as high throughput materials development. So what it means is that, let's say we have the periodic table, and you can think of like how many materials or compounds are possible from there. Now, essentially, there are quite a lot of 3D materials in bulk form that exist. However, the 2D materials which have been discovered are much, much lower compared to that. Okay. Now, as I said at the beginning, that it is not possible to go on and try to synthesize every single material, because that is like a humongous task. So what computationally people do is that they start with, let's say, certain 3D structure or primitive cell, what is existing there. And from there, people try to create a supercell and kind of map that problem into a 2D structure and kind of try to generate a 2D primitive cell out of that. And here you can actually see how does the material wise kind of like evaluation works out. So let's say you create some 2D primitive cell out of a 3D compound, and then you do some structural optimization, and then you perform this density functional theory calculation to know the energy. And from here you can actually, so of course, like you can I mean, it is possible to check the stability of the material. So like from phonon band structure it is possible. So I have not shown it here, but it is possible actually to do that. But here on interesting graph is plotted here. So for example, the binding energy has been plotted for different materials, and here you can see on the x-axis we have the change in interlayer distance. So that is like the distance between two neighboring layers. And here you can see there are basically three colored regions which are plotted here. So there is this kind of let's say saffron or let's say yellow colored region where the binding energy is quite high, and here you have this green colored region where the binding energy is intermediate, and in the blue region there are quite a lot of points which have a low binding energy. So from this behavior, what we can say is that if the binding energy is low, that means the material let's say is easily exfoliable, or in simple terms from the 3D structure, if I'm trying to exfoliate or detach a 2D sheet out of this, then kind of like the interaction force is small, so the binding energy is also small. As a result, it is easily detachable. Okay, so there is a higher probability of getting the 2D form of this structure. So for example, here you can see like this bismuth telluride, indium selenide, gallium sulfide, then molybdenum disulfide, etc. So this comes up under this category. Then you have this green colored region which is potentially exfoliable because the binding energy range is intermediate. So it might be possible, it might prove out to be difficult also. However, if in the high binding energy region, here we have quite a high energy, so this is quite tricky or difficult to exfoliate. So that way, if we have this information on a large cluster of materials, then from this graph one can actually target certain materials which have a higher probability of exfoliation, and that way people will not waste kind of like save a lot of time, and that is kind of going to help the materials discovery. Okay, so now so this is kind of like the, let's say, introduction part, or you can first part. So now I'm going to talk about some results which we have done in the past years. So the thing is that we have tried to use 2D materials in order to design some nano sensors. Okay. So this is basically, we have used these computational tools, mostly density functional theory calculations, in order to find out how different 2D materials can be incorporated or used to find or design a sensing device. And like since they are nanostructures, so they will offer a better kind of behavior. Okay, so now just briefly, what is a sensor? So we all know that we have basically 5 human organs, and with that we can basically sense different things. For example, like our ear is sensitive to audible signals, then our eyes can kind of detect optical radiation, our let's say nose can sniff smell, etc. So essentially, like these are the sensors which are attached to our human body, and we use them continuously, knowingly or unknowingly. So if we look at the work process, what it does is that there will be some physical parameter which it senses, and then it sends a signal to our brain. Our brain takes an action as a result of this, and that, let's say, determines the kind of final course of play here. Okay, so in real terms or in practice, what we can say is that if we have a sensing device, then that will kind of only sense. So the idea, what I mean to say here is that the sensing or a sensor is not a standalone thing, but rather it needs some other electronic device in order to kind of work completely. So we have like quite a lot of sensors in our day-to-day use. For example, we have our remotes, and then we have like smoke sensor, then optical sensor we have in our mouse. Then we have temperature sensor, that is the thermometer. Then we have a weight sensor, and then we have a wind sensor. Then our touch screen, that is a capacitive sensor. Then we have this barcode sensor, and then there are quite a lot like speed sensor, motion sensor, etc. So you can classify them in different ways. For example, like whether it's an active sensor or a passive sensor. Then operation wise also they can be classified. Now here basically, let's say if we are simply taking the example of our human eye, so that kind of like tells us how does a sensor kind of works. So here you can see that if we look at the entire spectrum, electromagnetic spectrum, then our eyes are only able to detect a certain region of this electromagnetic spectrum. So that is the visible region. So this is typically 400 to kind of 700 nanometer. So there is a big part of this spectrum which our eye cannot detect. Okay, so that is one thing, that a sensor will always have a particular range of operation. So it cannot indefinitely or infinitely work on any range. So it is limited over a particular range typically. And the second thing here is that, let's say if we are talking about our ear, so here you can see that this is basically the frequency of our again sound. So there is a certain region that is 20 to 20,000 or let's say 20 kilohertz. That is our human auditory range. So our ear can only listen to or resolve the signals which is in this particular frequency band. However, let's say if we are talking about other animals, let's say elephants or let's say cat, dog, or even dolphins, they can detect or listen to sounds which are in the frequency range that is outside that. For example, dolphins can even like detect ultrasounds. Our ear will probably will go deaf if we have something like that. So you can basically get the idea that like we have only certain specific frequency range over which our ear can function properly. Okay, and then the second thing is that the intensity. So here again, for example, like the intensity in decibel has been plotted, and there are several kind of like examples have been given. For example, if we are talking about whispering, then the typical intensity comes at like 40 decibel, and then in playground that is like typically 80 decibel, and when a plane takes off that is like 130 decibel. So here our ear can detect like safely 0 to something like 60 to 80 decibel, where we don't have any risk. However, if we are going above the range, then there is a possibility that harm can happen, and in some cases if the intensity is quite high, then some irreversible damage can occur, which means that probably like a permanent deafness or can happen to a person. So as a sensor, it will have a particular frequency range and a particular intensity. Okay, so that is something which is quite important. Okay, so now how we have designed. So in order to do that, like first I will introduce this concept of single electronic transistor. So if you remember that earlier when I was talking about this electronic trend, that is number of transistors are going to kind of increase and then the size is reducing. So here this is one of such structures where basically this is the alternative design of a transistor, but it can kind of like do a lot of functions. So essentially what happens is that, so here we have a source drain and a gate electrode, and there will be an island which is kind of placed in between them. Now in a typical transistor, let's say if you're talking about a MOSFET, then there will be a continuous channel which connects the source and drain, but here there will be no such channel. So this island will be slightly detached from them, and they'll be separated by something called as a tunnel barrier. So as a result, what happens is that now this island is kind of like a quantum dot. So here, as we explained earlier, that the density of states is very much quantized. So which means that the energy levels will only have certain discrete accessible levels. So whenever we are trying to get a conduction, then this conduction will also be quantized, which means that from the source only one electron will come, and then it will kind of arrive here, and then there will be another electron which will travel from here to here, and the potential of the island can be tuned by this gate voltage. So as a result, if we are measuring this drain current as a function of gate voltage, then we'll get these sharp conduction peaks. And every time there is a new kind of electron transfers from left to right, let's say, then we can say like the population is changing here. So if we want to look at a little bit into details, then here you can see this is kind of the equivalent circuit here. So this is the quantum dot, and there are these tunnel barriers which are on both sides. Now here this kind of this energy levels of this quantum dot, they are have it like well separated. And if we want to have a conduction, let's say from left to right, then what we have to do is that there this, let's say, left electrode has to be at higher potential compared to this. And let's say once that is done, then if we want the electron to move from the dot to the drain, then we have to kind of either increase the energy level of the particular kind of like, let's say, state, or we have to reduce the potential of the drain. Whatever we do that, basically there is an let's say potential difference that is being created, and as a result the electron will jump from here to here. So that is how the gate voltage plays a role. So every time it's like a opening and closing of the device. So here you can see like the population is kind of going step by step, and as a result this conductance is showing this discrete kind of peaks. And if you combine them, then what happens is that here you can measure this conduction map as a function of gate voltage and source drain voltage, and that will give you a kind of diamond shaped regions. So these are called as Coulomb diamonds. So here basically within the diamond the population will not change, but when you are going from one to the other, then the population will change. Basically the same happens from like whether you are moving from right to left or left to right. So here basically there are like a few important or interesting points which are written here, that here basically there will be a dot, and then that kind of acts as a channel, and then there will be a tunnel barrier. So here I didn't actually mention about it. It's Coulomb blockade. So basically the operation here, it is kind of like, also one can say that this is determined or like guided by Coulomb blockade. So what happens is, in simple terms, is that let's say the dot has a large number of electrons, and whenever there is an electron from left to, let's say, source to dot, it wants to come, then there will be some sort of electrostatic let's say repulsion that will be associated with some energy scale. So unless the electron from the left is having a certain minimum amount of energy, this barrier will not be overcome. So that is basically what we are calling it as a Coulomb blockade. Okay. So then we can actually talk about like different energy scale. So for example, like we can get the self capacitance and bias voltage, etc. Anyway, so essentially what happens is that here we get a discrete conduction, and that can be used for certain operations. So that we'll see how it works out. So here are a couple of experimental works on this 2D material based ACT. So here you can actually see from ETH Zurich, people have made this graphene based ACT. So there is a top gate, and then there is a chromium or aluminum contact. Then there are a few more, for example, in University Science and Technology China, they have also made a kind of like a double gated structure. And then there are other places also people have made these ACT devices from 2D materials. Okay, so now what we have done here is that, so this particular work is about DNA and RNA detection using a 2D material based ACT. So here you can actually see this is kind of like very colorful schematic of this thing. So you have source and drain electrode, and then we have an island. So this island is basically made up of a graphene and a hexagonal boron nitride heterostructure. And there are basically some like calculation parameters which are given here. So we have considered that gate is made up of certain metal, and then this dielectric layer has some dielectric constant. And then what we did is that we have kind of like first tried to understand the electrostatics. So what it does is that it calculates the energy of this system as function of different gate voltage. And here you can see there are different lines which are here. So they are corresponding to different charge states of the island. So here you can see like there is different slope of different lines, and this kind of behavior can be described with a equation which is given here. Like there are this total energy can be written down as a kind of like power series. So there are three terms. So there is a constant term, then there is a linear term in gate voltage, and there is a quadratic term. So if we do a fitting of this thing, then we can actually estimate these values of these coefficients alpha and beta. So here this alpha actually talks about like what is the direct coupling of the island with the gate. Okay, so it's like a strength of gate island coupling. So here you can see that so this BNG stands for graphene and boron nitride heterostructure, while BN means that boron nitride itself, and GR means that graphene. So we have kind of tried with 3 separate ACTs. So one is with graphene, other is with boron nitride, and other one is a combination of them, basically the heterostructure. And what you have seen that if we are using graphene, then the coupling is higher compared to the other 2 cases. And then here we have this beta term. So this is actually a measure of the electrostatic polarization. So it means that very simply speaking that let's say if there is some inhomogeneity in the layer, and when we are exposing it to a close by electric field, then whether any additional electrostatic polarization is being generated or not. So here you can see this term is quite small, and it does not vary that much with different cases. So it says is that the electrostatic polarization is not changing with a change in the configuration. Okay, so that is basically the electrostatic information what we get from here. Then what we have done is that now we want to see whether this kind of a device can be useful for a like a sensor. So here the first thing is that we have taken these different nucleobases. So there are 5 nucleobases like adenine, guanine, cytosine, thymine, uracil. And then we have kind of tried to place them on different locations on this structure. So there is some particular stacking here, like A stacking. And then we have tried to kind of place these nucleobases on different kind of locations, and we try to find out which one is the preferred orientation and kind of like other equilibrium properties. So here actually in the bottom panel you can see there are a few graphs. So here basically alpha is plotted for different nucleobases and without nucleobases. So essentially what we see is that even if there is a nucleobase, the alpha and beta, it does not change that much. Okay, so what we can infer from here is that the electrostatics of operation, it does not change even in the presence of these nucleobases. Okay, so now here actually you can see that there is a big table and there are few parameters which have been plotted. So the first one is the adsorption energy. So you can simply think of like this is the energy which is which talks about the strength of adsorption of that particular molecule on that island. So here, so basically this subscript A, it stands for adenine, and C for cytosine, G for guanine, etc. So here you can actually see that adsorption energy, and that is kind of, let's say, highest here for adenine absorbed graphene is highest compared to the other 2. And then also here we are getting this value here for boron nitride when guanine is there. So that actually we can compare, and then we can see which of these molecules or nucleobases is more likely to strongly bond with other. And then we have also estimated this like kind of distance of separation. And then here we can see that kind of varies between 1.6 to 2.4 angstrom. And I mean that kind of like, sorry, one is also here. So that kind of varies between this particular range. And then there is a charge transfer which has been estimated also. So what it tells is that, let's say, whenever there is a molecule that is being adsorbed on a particular 2D surface, there will be certain charge transfer. Now that charge transfer could be positive or negative, and that will kind of also kind of determine that what sort of adsorption is happening. So here what we have seen is that uracil shows maximum charge transfer on 3 host layers, and so if you have more charge transfer, then you can imagine that will be translated into the change in resistivity when you are doing an experiment. And in all the cases, what is observed is that there is no sign of any bond formation between the host layer and the molecule. So it indicates that this process of adsorption is physioadsorption in nature. Okay, and here in terms of bonding strength, this boron nitride offers, let's say, a higher one compared to graphene and this heterostructure. And here we have also tried to look at how does the density of states kind of like change in the unabsorbed and adsorbed configuration. And then here you can see there are 2 lines. There's a blue line and a red line. and that kind of is done for different nuclear bases. So this graph is only for boron nitride graphene, like the heterostructure. So if you look at these graphs, then you can see that at low energy, or let's say around the Fermi level, there is not that much difference in the density of states. But if we are going to high energy, then there is some additional peaks which are appearing. So same is true here. Here you can see around the Fermi level, they are kind of almost matching with each other. But at high energy, there is some additional peak which is appearing here. So that way we can say that since we are mostly interested here in this low energy kind of few electron volt around the Fermi level. So here we don't see much of change. That means the electronic property of the material, it does not change as a result of the absorption. So that actually is also confirmed from the physio absorption nature. So if it's a chemical absorption, then there will be bond formation and there will be some changes which will be observed in the density of states also. But here it does not happen. So that is why we don't see some observable changes here in the density of states. So okay, so now what we did here is that, so we have estimated this kind of charge stability diagram. So that is something which I have explained few slides back, that as function of gate voltage and source drain bias, if I plot this entire conduction map, so that will be a charge stability diagram. So here you can see there are basically different colored region which are kind of present here, and they are corresponding to different charge states. And so we have kind of like a defined few parameters like EC, so that is kind of charging energy. So it simply means that if I have to go from one charge state to the other, the island, then how much minimum energy is required. So here for BNG, like this like this heterostructure, and in the different absorbed configuration, the charging energy, one can actually see that this is typically around 1 electron volt or less than that. And if we compare, let's say, between different layers, then we can see that between boron nitride graphene and the heterostructure, it varies between like 1.2 to like 0.8 electron volt or something. Okay. So that is kind of tells that these host layers can be used for absorption. Okay, now then next thing what we have estimated is the switching performance. So that means, let's say, if we want to use such a transistor for switching, then how does the switching changes in the unabsorbed and absorbed configuration. So here you can see actually the switching voltage have been plotted for different cases. And here you can see that the switching voltage, it actually comes up in typically in millivolt. Okay, and the values are actually quite small when it is in the absorbed configuration. So it tells that basically like you don't need to apply a much like very large amount of voltage, but rather a small voltage to kind of do the switching in different configurations. Okay. Now then we check the sensing behavior. So what we did is that we have from the charge stability diagram. So that is from here we have taken the line scan, and these different line scans have been plotted in on top of each other under let's say different adsorbed configuration. So here, for example, this is the pristine case, and then there are like different molecules which are present there, and we have compared it. And here you can see basically, if you zoom in this particular region, then you can see that like there's quite a lot of separation between these different lines. So here it is plotted as function of source drain bias, and in the figure C, this is plotted as function of gate voltage. So in both cases, you can see these lines can be well separated. And if we are plotting the normalized conductance, then we can actually see that these lines are also kind of like we can identify each of these lines. So what essentially we mean by this is that let's say there is a specific nuclear base which is present, and the transistor will kind of operate, and it will give us a conduction peak, and that will appear at a specific voltage. Now, when there is another nuclear base that is present, then the peak is appearing at a different voltage. So essentially, we'll get a set of voltages at which the, let's say, first peak, second peak, third peak appears for a particular nucleobase. That is different from another nucleobase. So if we can kind of map these things, then we can say that if the peaks are appearing at this particular voltages, that means the nucleobase is likely to be adenine, or it is cytosine or guanine, whatever it is. So that way you can use it as a let's say sensor. So that's how basically we can identify different nucleobases. And as you can see that with only single molecule we have checked this thing. If we increase the concentration also, then we can do the same exercise. But here the detection resolution, it exists even at the single molecular level. So that is quite huge basically. Okay, so okay, so this is one thing, and then one additional work which we have done. So that is with like how these 2D structures can again be used, let's say, from sensing here. So that is basically, let's say, here we have taken a 2D phosphorine layer. So this is a phosphorus 2D sheet, and these edges are passivated with hydrogen. And then what we are doing is that we are measuring the, let's say, or we are checking the transport behavior of this particular system in the presence and absence of, let's say, an organic molecule. So in this case, it was a benzene molecule. So here what we see is that, so this is a kind of like small system. And if we check the current voltage graph, then we see that between the absorbed and pristine case, we see a measurable difference in the current. And the transmission itself is also kind of quite well separated from each other. So now that kind of tells us that there is a change in current or measured current or conductivity for such systems, even in the presence of this molecule. So as I said earlier, since like the surface to volume ratio is quite high, so that is why the kind of changes are very much observed. And then from here, actually, what we did is that we have tried to estimate the sensitivity, and that is through something called as a modulation factor, so which you have defined like at a particular voltage, eta. So IA, that is the absorbed case, and U means like unabsorbed, and IU minus IU, that is delta I divided by IU. So like a change in current divided by the original current that was kind of present there. So if we do that, then we have actually checked this difference under different conditions. So for example, we have done doping, and then we have kind of like different types of dopant, and then different locations, and then we have like applied strain, and there are quite a lot of exercises which we have checked. And then what we have seen is that like this sensitivity can reach quite high value, even up to like more than 500%. So that's why we can call it as like a colossal conductivity modulation. So here this is an kind of like phosphorine nanoribbon. So it's an armchair phosphorine nanoribbon. So here we are observing such a big conduction change even with one molecule. So such things can even be used for developing let's say any organic sensor, or even people can think of like a gas sensor, etc. So that's how these 2D materials can be used, and computationally one can actually try to estimate that what sort of behavior can be predicted from such systems. Okay, so with that, I'm coming to the end of the presentation. And so today we basically kind of gave an overview of like say some sustainability, then how materials development works, and computational development, and some results I have presented. So I would like to acknowledge the kind of support I received from IIT Patna, so from the department, and also from outside, kind of like other at the institute level. And I have specifically thanks to the students and also the colleagues, everyone, and of course the financial support which you have received. And thanks to DST also for offering financial support. So here are few publications which where we have basically reported similar types of work. If you are interested, you can have a look at them. So I have here presented probably one or two papers basically, but yeah, but you can actually have a look at others. They are like different types of, but kind of mostly focused on sensing these papers. So yeah, with this I would like to finish here, and thank you all for your time. Now I believe that yeah, I'm handing it over to the
Yeah,
organizers.
thank you, Dr. A. So I request the audience if they have any questions, they can go ahead.
Hello,
Are
sir.
there questions? Yeah, please go ahead.
Yeah, it's Indranil. Sir, very good presentation. And I would like to ask some questions about the experimental feasibility of this theoretical thing. Like, sir, is ACT device are experimentally applicable? Like, is there any work this type of
You mean
experimental work?
on 2D ACT or just not normal ACT?
So normal like quantum dot and then
Ah,
other.
yes, yes, I
Yeah.
have done. I myself have done.
Yes, sir. Yes, sir. So, sir, now how the gate is the gate is also separated from this quantum dot, means like source and drain.
Very good question, actually. Very good question. Okay. So, see, the point is that in like whatever we are drawing it in a cartoon, that is not actually going to look like in an experiment, right? So, essentially, what happens is that, let's say, what is a quantum dot? Basically, it is like, let's say, an electron rich structure, right? That is let's say it could be metallic or semiconducting quantum dot. So let's say very simplistically, if we take like a metallic dot, okay, so there will be some certain, let's say, number of electrons which are confined in a confined space, right? So you somehow have to create that kind of a structure, and then so very simply what you can do is that let's say one can do it through ion implantation. Okay, suppose like you have a substrate or something, and then in that not a metallic substrate, but like let's say silicon or something, and then you do some ion implantation at some particular energy. So what will you end up with is that is a kind of confined or a small area where these ions will be trapped, right? Okay, so that way you can create a quantum dot. Or alternatively, if you are working with 2D, then what you have to do is that you have to somehow isolate that kind of 2D structure itself. So either you have to pattern it, or you have to somehow cut it, and then kind of like there will be no direct electrical contact between the dot and the electrodes. So you have to keep
Okay.
some sort of barrier. So that could be an oxide layer. Like it's a tunnel barrier, right? So the I mean the conduction happens
So
through tunnel.
means also with the gate, this same thing is
Ah,
applicable.
right. Yes. So gate is also, see, gate is little bit kind of simple, because any gate you have to put a dielectric layer on top,
Yes, sir.
right? So yeah, so you can
Hmm.
think of a gate is also separated, but there has to be a dielectric layer, which is again like alumina or something you can think of. So that is
Okay.
another kind of insulating layer which is separating this. So yes,
Okay,
so
sir.
yeah, basically it has to be separated, but it cannot be like vacuum.
Oh, okay, okay. Means some insulating layer, right?
Ah,
Or
right.
semiconductor layer.
Right.
Okay, okay. I got the
Uh,
point.
So if you
Thank you.
think of like a, like magnetic tunnel junction, so
Uh-huh.
there you have to put a oxide layer between two ferromagnetic layers, right? So otherwise the
Yes.
tunneling will not happen. So the thickness have to be
Okay. Means
small.
in vacuum it will not happen, right?
See, in
Uh,
calculation when we do with imagine, but in reality, in practice, we cannot have vacuum, right?
yes, so that's why I asked this. Like in
Okay.
reality, if it is like that, then it will be tougher to us, like to figure out the structure and to implement it. But
No,
if
you
we
have to.
use the insulating layer or semiconducting layer, that is fine. Means someone can do this, and the
Yes.
tunneling can be sensed by this layer also. Like
It will
through this
happen through
layer,
the.
the tunneling can be sensed.
Yes. It will happen through the layer.
Yes, thank you.
Yes. Yes.
Okay,
Any
are
other
there
questions?
any further questions? Yeah. I request the participants to unmute and ask any questions if they have. Okay, other members from IIT Patna, there I can see lots of people have joined. Hello.
Hello.
Yes, please go ahead. I think somebody is trying to ask a question.
Hello? I don't hear anything. Hello?
I don't see anyone unmuted, so looks like it's a stray pickup from somebody who has kept it on hold. I think Pratap
Okay.
Singh. Yeah, okay.
Hello, sir.
Yes, yes.
Sir, actually, I was trying from my laptop. It was audible, I think. So, hello.
Yes, yes. Listening. Yes.
So, sir, actually, in case of computational methods, as you told, like firstly, as there would be, we write the eigenvalues means for kinetic energy and potential energy of any structure in order to, make the Schrodinger equation, and then that would be solved by computation method.
Mhm.
So, sir, in case of computational methods, as you know, we are not solving them analytically. So there are so many approximations are being, put in order to solve them computationally. So as we are doing simulation in atomic scale, where there is the quantities are of the level of the order 10 means of Planck's constant or like. So, sir, how uh, how are these approximations to be are made we how do we make that those predictions accurate, that I want to know, because once you solve, even the computer doesn't give the exact value. There is approximation all the time. Somewhat approximate mason is there, because all equations are being solved by computational methods as.
Mhm. Okay.
So,
So,
sir, how
yes, yes. Finish.
So, sir, how are these, approximate, how do we make them accurate? I mean, how do we make those simulations accurate? That I want to know, sir.
Okay. So, I mean, it's a very like a problem which is there from the beginning itself. So the first thing is that I mean these calculations do work well with atomistic systems, because here you deal with a certain number of atoms, let's say few hundred or like few hundred atoms maximum. Hmm.
Yes, sir.
So we cannot like say that like okay, in reality you can imagine like few hundred atoms are like very few, right? Okay, but for
Yes, sir.
2D system kind of like quantum dot, that's still kind of a somewhat okay approximation. But if you're talking about let's say 3D structure itself, anyway, so this I mean in that sense it is more realistic to kind of go with a low dimensional system here. Okay, now
Yes,
coming back to the approximation, yes. So these are see again at the end their approximate methods and their calculations. Okay,
yes,
so
sir.
here actually I didn't show, but okay, one graph I have showed. I think that is it's kind of like unless you are doing the experiment, you will
Yes,
not
sir.
know what is the exact behavior. So the best
Exactly.
thing you can do is that you can predict, let's say whether the material will be semiconducting or insulating or metallic or it will be magnetic or not. So those kind of behaviors so are kind of robust, which means that whatever you see from there, they will almost, I mean, they almost come out to be true with experimental observations. Okay. Now,
Yes,
what
sir.
is different? Difference is that let's say the value of band gap. Whatever you measure, because you are taking certain approximations, right? So you are
Yes, sir.
using certain functionals, and that might not exactly match with your experiment. Now, whenever you are doing an experiment, let's say you are, I mean, there are couple of reasons. So first of all is that in the simulation or calculation, you are starting up with an ideal system,
Yes,
right?
sir.
So whatever your primitive cell, your kind of unit cell structure, etc., they're ideal. But in experiment, your system is not that much clean.
Exactly.
Right. So there will be specifically for 2D systems, there will be quite a lot of, let's say, functional groups and other structures. Like even you don't know how many numbers of layers are there. You'll probably know, but it's not like 100% for surety you can say this is the particular shape of this thing, right? So you cannot see the starting system itself in both cases are different. Then how can you predict that the behavior will be same? It will not be, right?
Yes, sir.
So that difference will always be there. But what is observed is that the trend matches. For example, let's say for molybdenum disulfide, somebody has predicted, let's say 1.8 electron volt band gap. Experimentally, people have seen like 2 electron volt. Okay.
Yes, sir.
Under certain doped configuration, that band gap probably have dropped to 1.6 electron volt. Huh. Then calculation probably gives also something like 1.4 electron volt. So you see the trend stays same.
Yes,
The
sir.
value might be slightly different.
Okay, you mean the graph, the curve, this shape is
Right,
going
right.
to be to follow the experimental ones.
Right, right. You see, so the
Okay.
overall trend, if you do the calculation properly, like with like good approximations and like carefully, then you are likely to get kind of like, let's say somewhat a agreeable behavior between different cases. But
Yes.
I mean, direct one-to-one match you can only see between once you have the experiment. And having said that, there is no guarantee that you repeat the same experiment, you will get a same value.
Yes, sir.
You understood? So
Yes, sir.
itself, you don't know which one to trust. So unless like there is
Correct.
like large number of experiments, people have done the same thing, like probably they're measuring band gap for like 1,000 times, then only people can come up to some sort of predictions. Okay, out of 1,000, maybe 800 times people have observed this value. So this is the mean value or something. So that's how basically it can come up. But otherwise, what you can say is that since these are kind of approximated calculations, so you can try to make it as close to the experimental value as possible. But otherwise, in reality, what is observed is that the trend it offers, that kind of matches with this thing. The exact value might be slightly different.
Yes, sir. Sir, another thing, sir, all the time, as we maybe we are not considering the temperature here in case of simulation. So would I feel like electron, some would changes should be there because of temperature, because all the time the experiments are going on, some temperature is there because that also defines the properties of the material at that particular temperature, whether it's reacting to particular compound, its affinity to particular uh, species.
Yes, you are correct, basically. So here, these are mostly ground state calculations. So they offer, so you imagine, like suppose you are measuring the band gap.
Yes,
Okay.
sir.
I mean, do you really say band gap at 500 degrees Celsius is this much? You say like silicon has this much band gap, right? So you kind of go with that ground state value itself. But if in terms of temperature, if you do it, then you have to only theory calculations are not enough. There are some additional terms, so you have to consider the Fermi factor, or you can do like there are other calculations which you can do for doing calculations. Let's say knowing such behavior at elevated temperatures.
Yes.
Okay.
So would you repeat, sir? I couldn't hear properly, sir.
What I meant to say is that, see, typically the results which you are getting here, they
Yes.
are mostly, let's say, equilibrium calculations, like ground state behavior you are getting. So let's say if you are getting the band gap value of something,
Yes, sir. Yes,
then
sir.
I mean people say that this material has this much band gap. They don't say the band gap at this particular temperature, right?
Yes, sir.
So that's what I'm saying. That's why the observations which are made from these calculations, they kind of go with that way.
Okay, with the
But
equilibrium
in
conditions, which you mean?
right, if you let's say want to go with an exact calculation what happens at elevated temperature or something, then you have to consider, let's say, this Boltzmann factor, and then you have to, I mean there are other calculations which you can do.
Yes,
For
sir.
example, like there are, yeah, I mean, Monte Carlo simulations you can do. Then there are like TDDFT that is there. Molecular dynamics also in some cases that is there. Like if you want to know whether the structure changes, so there are ways basically.
Yes.
Okay.
Okay. Thank you so very much for clarification.
Thank you.
Thank you.
So, Dr. Ray, if I may just add, Kashti, when you are asking a question regarding a computational technique, we also have to have this hindsight that whenever we make a model for analytical calculation, even that is approximate. No model truly captures everything about a real experiment. So you only perfect it based on experimental data, as Dr. Ray suggested, right?
Yes,
And as far as this point of high temperature, so he already mentioned a number of techniques, like among them this non-equilibrium green function technique is yet another one.
Yes, sir.
Right? Yeah.
Yes.
Okay.
Yes. So yeah, so I actually want to add one more point here. So you see, like, I mean, the kind of like powerful of this technique is that, like, let's say whatever, like this Hartree-Fock or tensor functional theory in that sense is that, like, this is a first principle based technique. So you are not kind of starting with a theory itself.
Yes,
Okay.
sir.
So,
Yes,
so
sir.
basically you are starting itself with a very fundamental equation.
Exactly.
Which is kind of valid. So that way you are not like, let's say, taking something. You understand what I'm saying? So that way you can say that, like, you are kind of in a way, let's say, more organic in that sense. But of course there will be differences.
Exactly. So,
Yeah, so if there are no further questions, let us thank
thank you so very
Dr. Ray
much.
again. Yeah, thank you so much, Dr. Ray, for your time and for elucidating this area so neatly.
Thank you.
Yeah, thank you so much.
Okay,
So,
thank you.
so Dr. Kar, shall we close this meeting now?
Yeah, it's okay. It's okay.
Yeah, you want to convey something to the candidates right now? Tomorrow is the last day, so they must attend all the sessions. Right, it is very important for them. And also tomorrow they also have to give a short evaluation test. So we will see, like we'll contact the AICT with all the information and see what can be done after that. Yeah, so please attend the evaluation test. Thank you.
Okay, thank you. Bye.
Yeah, thank you. Thank you so much.